All right, we've got our equation at the top. If we call that number 1, and what we're trying to work out is the enthalpy change, number 1 for that one. Just to make it a little bit easier for me to refer to them, I'm going to call those 2 and 3. And the enthalpy changes here, if you needed to, you can refer to them as R2 and R3. Those are the values over this side, so that's R2, that's R3. And this sort of approach is what you're going to need for the assignment. So where do we start with this? We've got to work out the enthalpy change for reaction 1 given the 2 that we've got there, 2 and 3. You can start in all sorts of places with this, but I'm just going to talk you through it for those who might have missed it, those who weren't that secure on it, and then I'm going to give you another one to do for yourselves. We start by looking at what's on each side of our original equation. So equation number 1 has got N2 and O2 on the left, and it's got the NO on the right. And if we look at the equations we've been given to work with, well, equation 2 has got oxygen on the left, which is quite a promising start, and it's got nitrogen oxide on the right. So that looks like we can leave it that way round. However, it looks like we've got rather too much of it. We're going to look at the nitrogen oxide there, and we're going to need to divide that by 2. If we divide equation 2 in half, we'll be part way there. Now, if you have a look at equation 3, we've got oxygen on the left again, which makes you think, well, yeah, all right, well, we want oxygen on the left, but we've got nitrogen on the right. So we're definitely going to have to turn that one round. So number 3 is going to have to be flipped. So the first thing we might be doing is halving number 2 and flipping number 3. However, we're going to need to do something else to number 3. Because we've halved number 2, we've got 2 NH3s on the left and 3 H2Os on the right. If we halve it, haven't we? Never mind the other bits. If we flip number 3, we're still having 6 H2Os and 4 NH3. So we're going to have to halve that one as well, so things will cancel out. All right, this might not make much sense until it's written down. Fingers crossed it does. All right, so if we half equation 2, we get 2 NH3s plus 5 over 2 oxygens will give us 2 NOs and 3 H2Os. That would only take half the energy, of course, which is what we're going to do in the end. So that's a start. With number 3, we're going to have to flip it and half it. So flip, it is the word we seem to use. So flip and half 3. I've got to do it now all in one go. If we flip that, we get the nitrogen and the water on the left, and if we halve it, we get 1 nitrogen and 3 waters. And we end up with our ammonia, our NH3 and our oxygen on the right, and if we halve that, we get 2 NH2s and 3 over 2 oxygens. And it depends how good you are at fractions as to whether you'll be able to cancel those out. We now use the simultaneous equation approach, and we're just going to add those together, because this is what we mean by Hess's law. This is following the other route. We're following half of equation 2 to one intermediate situation, and then we're reversing half of equation 3 to get back to where we wanted to. So if we add up those two, we get 2 NH3s. Let's add up, let's go as we read them. 5/2 oxygens, 5 halves if you like, an N2, 3 H2Os over that side. All right, that's adding up everything we've now put over there. On the other side, we've got 2 nitrogen monoxides, we've got 3 waters, we've got something I've put up wrong, haven't I? That should be NH3. All right, so 2 NH3s and an oxygen. Right, how are we doing? No, we haven't got an oxygen, have we? Lost my fraction there, sorry. Let's redo that. 3/2 oxygens. I was just thinking that's not going to cancel out. Okay. If something appears on both sides, you can get rid of it, because if you put it in and you get it out, it didn't react. So we can lose. Ammonia on this side cancels with 2 ammonias on this side. We've got 3 waters on this side cancelling with 3 waters on that side. We've got a single nitrogen on the left, which is okay, and 2 nitrogen oxides on the right, which is okay. And then we've got 5/2 oxygens on the left, 3/2 oxygens on the right. So we can get rid of the 3/2, bring that down to 2/2, so that's 1 oxygen. All right, so we have our equation 1. A single nitrogen there, a single oxygen there, and then 2 nitrogen oxides there. So we know we've done the right thing. Now the enthalpy change then for the first of those reactions for equation 1 is half of whatever we had up there minus 1170. Sometimes easier just to put it in brackets to make it clear. And then minus a half. All right, we're adding them together, but it's plus minus a half of the other one, minus 1530. And I will let you work that out. I'll need to check an answer sheet for myself for that. Right, let me move that out of the way. It doesn't want to go. Okay, if we calculate that through, and you do have to be very careful with your minus signs, you end up with 180 kilojoules per mole for that. This is exactly the sort of thing that you're going to be doing in the assignment, that you're going to be actually working out practically the 2 enthalpy changes you've got to use. So what you're going to do tomorrow is a reaction between sodium hydrogen carbonate and hydrochloric acid, and work out the enthalpy change for that. And then you're going to do one between sodium carbonate and hydrochloric acid, work out the enthalpy change for that. And from those 2, you will then be able to manipulate them in a similar way to that to work out what it would be, what the enthalpy change would be, to go from sodium hydrogen carbonate to sodium carbonate, which is something that we can't do. It's just not something we can measure very easily. So that's just to remind you what we have to do. It's a matter of just gathering the right bits from the equations that we're given onto the side that they are found in our the one we want to work out, the one we're looking for. Okay, there's another one here, so one more to work through just to be sure that you get it. Whoops. All right. Can you see that all right? This time we've got 3 equations to do it from. All right. You're looking to work out the change going from, and I will use colour so they stand out, 2 carbons plus hydrogen gives you C2H2. C2H2 is ethine. It's one we haven't met. We've done the alkanes, mentioned the alkenes. These are alkynes with a triple bond in them. That's the one that we're trying to work out, all right? So that will be our delta H naught R1. We're then given 3 other options to work with. The second one is carbon and oxygen, giving us carbon dioxide. And our delta H naught there is minus 393, whoops, 3.5. All right, I'm not putting all the units and symbols and things in. I just want to keep it clean for the board. Equation 3 this time, I don't know if we call that 1, is going to be hydrogen plus half O2. All right, don't be scared of fractions in this one. Gives us water for a change of minus 285.8. And then we have another one in this example where we've got 2 C2H2s. They're on the wrong side for what we want. Plus 5 O2. So this one's going to definitely be a little trickier, isn't it? Gives us 4 carbon dioxide. Okay, that's a combustion. In fact, C2H2, it's got 2 carbons. Yes, it's ethine, but it also would have started with acetyl in the old naming system, so that's actually acetylene. So have you ever heard of acetylene welding torches and things like that? That's acetylene. So that's the burning of acetylene at the bottom there. All right. So our change there, and not surprisingly, burning acetylene is going to give us quite a lot of energy, 2598.8. All right, so we're trying to get to equation 1 using 2, 3 and 4. So here is our delta H naught R2, our delta H naught R3, and our delta H naught R4. All right, I'm going to let you play with those for a bit and see if you can rearrange them to get everything on the correct side. What you're looking for is gathering carbon and hydrogen on the left and the ethine, the C2H2, on the right, using those 3 equations. It's a bit like a puzzle, isn't it? You know, you just got to solve this puzzle and it all just falls into place. All right, looking at what we've got here then, we need to get carbon on the left, hydrogen on the left, and the C2H2, the ethine, on the right. So having a look at equation 2 then, we've got carbon on the left, okay, but not enough of it, and carbon doesn't appear anywhere else, so that's fairly suggestive we're going to have to double equation 2. Equation 3, we've got hydrogen on the left, and that's not appearing anywhere else, so that's looking okay, and it's in the right quantity, so that's looking like it could probably be left as it is. But equation 4, we've got the C2H2 on the left, and we want it to be on the right. We've also got 2 of them. So it's looking as though we double equation 2, leave equation 3, and flip and halve equation 4. Does that tie up with everybody? Yes? Okay, so we're in with a chance on that one. I just noticed I've done something very strange down at the bottom of this board. I've inserted a whole load of zeros by leaning on the keyboard. Oh, that's an awful lot of zeros. All right. Okay, so let's work this through then. We have number 2 then is going to be doubled up to get the 2 carbons on the left. So we end up with 2 carbons plus 2 oxygens gives us 2 carbon dioxides. Number 3 is okay as it is. So we have hydrogen, half O2, and on the other side, carbon dioxide. No, we don't. That would be magic, wouldn't it? Hydrogen and oxygen making carbon dioxide. Let's try for water instead. And then, for number 4, to get our C2H2 on the other side, we flip. And to get it down to 1, we halve it. So flip and half. So we've got, if we turn it round, we get our carbon dioxide on the left, and that will be down to 2 of those, won't it? And we will then find that we've got a single C2H2 and 5/2 oxygens. And so if we add that lot up, hopefully we will have 2 carbon, 2 oxygen, a hydrogen, half an O2, 2 carbon dioxides, and I've started too far to the left. On the other side, 2 carbon dioxides, that's handy, a water, C2H2, and 5/2 oxygen. So a bit of cancelling here. What can we lose? What's easy to lose? Carbon dioxide is very easily lost. Yep, 2 of those, in and out. We've got, I've lost something then, haven't I? What have I done wrong? Okay. What did I... Right, sorry, yes, I lost 2 H2Os on there, was it? Yeah. Right, yeah, sorry, lost those. Yeah, I was wondering what had happened there. Right, so if we flipped that and halved it, I should also have a water over here then, shouldn't I? Yeah, that's one reason for doing this adding up at the end, is to make sure that, you know, you have covered everything. So I should also have, in my green, I should have an H2O there, shouldn't I? Right. You know, if you go straight for the numbers, yes, you know, if you've written it out right, it'll be okay. But, you know, to make sure everything cancels, the safe way is to write the equations out. So we can now lose the water, okay? We should be able to lose some oxygen, I think, shouldn't we? What have we got on the left? We've got that one and that one, which together make 2.5 or 5/2, yeah? So that and that will cancel out. Hopefully we're now left with what we need. So we've got 2 carbons, an H2, giving us our C2H2. Yes. Okay, so the check works out, but at least, yeah, it does when you've corrected it. And our calculation, therefore, will be to get our delta H naught R1, we're going to need to double the value for 2, aren't we? So that's 2 lots of -393 minus 393.5. We need to add on to that 1 lot of delta H3, R3, sorry, minus 285.8, minus 285.8, and then the messy one, flip it and halve it. So we're going to have minus a half there. So minus a half of our, oops, minus 2598.8. Minus 2598.8. All right, so we've done to our energy values exactly what we've done to the equations, and that comes out at, I'm sorry, I forgot what the number was, 266. Sorry, that was all at once. 226. Thank you. 226.6 kilojoules per mole. Right. Yeah, the one you've got to do will actually be simpler than these. So you're experts at these now, really quite complicated ones. But yeah, the practical one is not so hard, and I'll remind you how they work again for that. I got these obviously off the internet, and the document actually came with some handwritten solutions to this. So I pasted those on the next board, and yeah, they were a little bit messy looking, but just to prove that they did come out like that, those were the answers that the original tutor actually put on there. So yep. All right. You see that? You see, that is the way of sorting them out, is to actually multiply the equations up, then multiply the numbers up. So you've got a bit of a check there, but yeah, a tad on the messy side. And if you're writing it in an assignment, you've got to be really careful how you lay this out. All right. Okay, well that's sort of checked back to where we were last time. Okay, next thing then. Calculations using enthalpy change of formation. So using oops, sorry, enthalpy changes of formation. And so those will be like that. So you've got your standard enthalpy change, that means, and then the subscript F is formation. All right. So far we've had the R for reaction, we've had C for combustion. There are a load of others, and that's part of what I've got to do next week, is talk for a whole lot of other enthalpy changes. And this is all thermodynamics, thermo meaning heat and dynamic meaning change. So it's about energy changes in chemistry. A recap, because we have mentioned this in the first unit, that it's the enthalpy change when 1 mole of a compound is formed from its constituent elements under standard conditions, with all reactants and products in their standard state. So I'm going to write that up just as a reminder. The 1 mole bit is important. It means you can't use just any old equation. It's a bit like the combustion one. It's, yeah, that, all right, that we've already got up there, is enthalpy change when 1 mole of a compound, so you'll have to use fractional equations quite often, is formed from its constituent elements under standard conditions and all reactants and products in standard states. Now you can imagine that doesn't actually happen very much. You know, if you just put some carbon and oxygen on your desk, it's not suddenly going to turn into carbon monoxide or dioxide. You know, it's very much a theoretical process, but It's actually a really useful option for checking all the others that you've got. You know, all the other ways of calculating enthalpy. Mind you, the bond energies one is useful as well, but there will never be complete agreement between the different measures. That's just the nature of stuff, really. Too many sort of variables and different types of enthalpy change. Any sort of change, whether it's a change of state, a change in a reaction, anything like that, is going to involve energy moving. It takes energy to break bonds. It releases energy when bonds form. And you can look at that in all these different ways. Yeah. Well, the bond energies approach it's a bit of a it's a fairly basic way of doing it, because not all bonds are equal. For example, you know, if you've got, let's say, a water molecule, I'm not sure if I'm choosing a good example, and you look at the amount of energy it takes to break the hydrogen and oxygen apart, it might take a certain amount of energy to remove the first of the hydrogens, but then it can take a different amount of energy to remove the second hydrogen because you've altered the molecule. So bond energies is very much a sort of average, you know, it's a best guess using average values. And it's just that we have various options because of all the different reactions that have been you know, energy values have been recorded for. That we can look at it in different ways. I mean, so far we've only really had three. So we've had enthalpy change of reaction, we've had bond energies, we've had combustion. So we're moving on to this one. Oh, there's you know, we could have another dozen different sorts of energy change that describe ionization energy. We actually mentioned that in Unit 1, didn't we? Oh, energy of vaporization we had in that last assignment. I'm sure you don't want to even think about that one. So anywhere that energy is involved, you have an enthalpy change value for. So yeah, it's just to measure different aspects of chemical change, really. Right, now, given that definition, what do you think the enthalpy change for carbon is? No, as a number. Is carbon a compound? No, it's an element. There is no value because you can't make an element from its constituent elements. So this is a really, really important point. Wherever you get elements in an equation, the enthalpy change of formation is 0 because you don't make them from elements. They are there. So that's why this is quite useful, because wherever you've got equations that involve elements, yeah, you can work out the rest of them fairly easily. So, important note, right? Note well. So delta H naught F for elements is 0. Okay, let's go into an example. I'm not going to use the book just for the time being, although these numbers might match up with that. Whoops, lost them. Now, if we look at some example compounds, and the enthalpy of formation. I'm just using ones that I've got written in my notes, so I'm not referring into the data book for this. I got these were an example in a textbook. We're going to look at sulfur dioxide as a gas, because that's its standard form, hydrogen sulfide as a gas, because that's its standard form, and water as a liquid. And the enthalpy change of formation here, when you form sulfur dioxide, from which elements? Oxygen and sulfur. Simple as it is. No, it literally is as simple as that. So when you form sulfur and oxygen into sulfur dioxide. Not that you can just do that, you know, you can't just put a piece of sulfur in some oxygen and hope it'll happen. The energy change, if you could do it, and some of these will have been done. I'm not going to put all the units in there, we'll put them up there. Kilojoules per mole is at least consistent, isn't it? So minus 297. For hydrogen sulfide, which would be made from hydrogen and sulfur, yeah, we're getting it, is minus 20.2. And water made from, yes, hydrogen and oxygen, the enthalpy of formation 286. All right, now those might not match up exactly with what's in the data book. It will depend on the definition of standard conditions and average values and all that. We're going to calculate using that, and this is where the thermochemical cycles come in. We're going to calculate the enthalpy change of reaction for this equation, where we start with sulfur dioxide, which is a gas, and we react it with 2 moles of hydrogen sulfide, a gas, and we can produce 3 moles of sulfur, which is a solid, and 2 moles of water in liquid form. Okay. Now what we've got to consider here is what elements are involved. Well, we've only got 3 elements involved here, haven't we? We've got sulfur, we've got oxygen, and we've got hydrogen. Yeah? So all of that we've got on the board there can be made from sulfur, hydrogen, oxygen. In theory. All right? This is not something you can just do. I mean, calculate delta H R for this reaction, okay? But using the delta H F values, all right? So the elements involved, well, let's see what we got. We've got, well, on each side, does that equation balance for a start? It certainly does. How many sulfur or moles of sulfur or sulfur atoms would we need altogether? There's 3, yeah, 3 on each side. There has to be in a balanced equation. So we've got 3 sulfurs. Whoops, I was going to put gas for that. That is an S, that's not a G. How much hydrogen have we got? We have 4 atoms, but hydrogen doesn't hang around as atoms. Hangs around as an element, it's 2H2, isn't it? Yeah? Would be a gas. This is in their standard states, remember, so we couldn't have just atoms. Similarly then, how much oxygen on each side? Yeah, so we would call that O2, because in its standard state it is a gas and it's diatomic. It's a molecule made of 2 atoms. So that summarizes the elements on the left. It also summarizes the elements on the right. The delta HF values that we've got up in that table there tell us how much energy it will take to convert some of the sulfur and the oxygen into sulfur dioxide, some of the sulfur and the hydrogen into hydrogen sulfide. Doesn't tell us how much energy it will take to go from sulfur to sulfur on the right, because that just stays the same. But it also tells us on the right how much energy it takes to go from hydrogen and oxygen to water. Right, so we can do something with those values, and this is where we start to need the thermochemical cycle, the 3-sided approach to this. Right. If we start with our reactants then over this side, I'm going to have to rewrite the equation because it disappears off the board. So we've got our SO2. I'm going to miss out the state symbols again because it's just going to get in the way. So this is what we started with at the top. Here's the value that we're trying to calculate. You'll see how easy this is in a minute, don't worry. On our other side, we've got solid sulfur and water. Oh, I did, didn't I? That's me not being consistent. No state symbols on the left, state symbols on the right. Okay, right. What we do now is to put our elements at the bottom. So this is where the triangle is going to come in down here. So our 3s, let's put the state symbols with them at least. We'll put them as plus 2H2 in gaseous form, plus an oxygen as gas. The easiest way to think of these is with those modelling beads, the molymods. If you made a model of sulfur dioxide and a model of two hydrogen sulfide molecules, how would you turn those into sulfur and water? You'd take them all apart, wouldn't you, into yellow beads, red beads and white beads, and then you'd put them back together again. Yeah? And that's really what we're saying here. Theoretically, you could pull all the molecules on the left apart into those atoms. You could pull all the molecules on the right apart into those same atoms. But what we're actually looking at in terms of formation energies is take the beads at the bottom, three yellow ones, 4 white ones and 2 red ones, and stick them together into the compounds that are in the equation. So if we were to go from this lot, all of these, up this side, if we were to make sulfur dioxide and 2 H2S's, the energy involved over here is value for sulfur dioxide, which I've given as minus 297. And then we need 2 lots of, that's it, plus 2 minus 20.2. So that's not a very tidy way of writing it, probably. And so that's the energy involved on that side. Quick on the calculator. All right, minus 297 plus minus 40 point something. You should be able to do it in your head, really, shouldn't you, that one? Is it minus 337.4? Right. So minus 337.4. Of course, I keep, avoiding any detail that gets in the way, but we'll put the units there. So that's how much energy would be released if you turned those elements into those compounds on the left. However, what about if we went the other way? If I'd given each of you a set of 3 yellow beads, 4 white ones and 2 red ones, some of you might make what was on the left, some of you might make what was on the right, and some of you might make something completely different. So if we were to go that way instead, okay, so what's the enthalpy of formation for the sulfur? 0, yeah. Worth just reminding ourselves, so we've got a 0, and then we need to add to that 2 lots of the formation for water. So 2 lots of minus 286. So what we should have over here is minus 572, exactly. Okay, so how can we now work out the standard enthalpy change of reaction? Sort of. Think about the root. This is where the root becomes important, because you're going to, you can look at it as a simple take one from the other, but I want you to visualize the route that you're taking, because what you would be doing is if you had these, you would take those ones apart, wouldn't you, into that, but then go up there. All right, so you want to, it's the flip. It is. Yeah. All right, so because it's minus 337.4 on this side, going the other way will be plus 337.4. So if you just follow the red route, you have the enthalpy change overall then. The trouble is I keep losing the... I'm writing too big, or the board's not big enough. Our enthalpy change of reaction for this is, it's the plus 337.4 that we've used to break our reactants into their elements, plus the minus 572 that we get as a result of forming the products. Sounds about right. Minus, hang on the other side. Oh, I haven't actually even worked it out on here. Brilliant. All right, what did you say? Minus 234.6. Yeah. All right. So it's not particularly complicated, is it? But you can see now how those triangles work. But you'll actually find it's usually written as the products minus reactants. Yeah, because it would then be plus. That would give you the plus bit. But actually drawing it out like this actually helps you to see what you've got to do, and you can follow that route. And if you think of those molymod beads, you can visualize what's actually happening there. Yeah, the triangle is particularly good for this, and you've got a couple of examples in your assignment to do, and I would recommend drawing the triangles. It's a bit fiddly, I must say. On a word processor, trying to draw something like that is quite tricky, but it's, you need to do it really to show that you understand what's happening. You could just do the calculation and write down the answer, but you know what this is about in terms of grading, showing your understanding, that you can see how that will work, can't you? Right, so I'll give you an example and see if you can work one of these out on your own. Oh, I'm releasing you into the wild on one of these quickly. So, I've got several. Don't know which one to start with. Yeah, I mean it is, it's still using Hess's law, isn't it? So that route 1 is the same as route 2 in terms of energy change, and you can write them out quite elaborately. I might just do one more to show you a thorough way of writing it out, perhaps. No. We'll come back to that if we need it. Okay. Example 2. I could have just put e.g. Okay. Right. Ethene can be produced. So I don't want to just give you the equation with this. I want you to at least start with that by an elimination reaction, not one of the types that we did. All right, elimination reaction does what it says. It removes bits of ethanol. All right, you'll sort of have to work out what's happening to start with. I don't want to make it too easy. Here it's just going to be calculate the standard enthalpy change of reaction using standard enthalpies of formation. Let's see how we get on with this. This could take a little while to sort out. First thing you need to do is obviously try and work out what the equation is. So I'll just give you a minute to see if you can work out what happens in the reaction first. Okay, if we identify, sorry, the AM, amorphous. Amorphous means it doesn't have one defined state. So when, yeah, if you see that in the book, it's well, it's not that it's not defined, it's just that it doesn't fall into one of the main categories. Generally, the word in everyday language just means shapeless, really. Well, morph means shape, and amorphous, sort of without shape. So our elements, yeah, we'd have 2 carbon, and then it makes it a bit bulky, but for our standard state, we are supposed to write S, comma, graphite, which is a bit annoying because it takes up a lot of space. What else are we going to put in for our elements? 3 H2s to cover our 6 atoms, but standard state hydrogen gas. And what else do we need? Sorry? It is a half an O2, yes. Yeah. Okay, so that's our next step. All right, so we've got our products on the right, our reactants on the left. If we put our 2 arrows in, so we could form either what's on the left or what's on the right, rather than writing all the numbers in next to the arrows, because when you do it on a word processor, that just gets messy trying to line everything up. On the left-hand side, you could put that we're just recognizing that this is the formation, sorry, the enthalpy change formation for reactants. And then you can total it up underneath. All right, you can identify reactants and the delta H naught formation products on this side. Okay, and then underneath you can start with your delta H naught F reactants you can calculate, and it does make it somewhat tidier. And then similarly your delta H naught F for the products. All these, this is really subscript for those. I tend to write them fairly big so you can see them. So once you've worked those out, you can then do your calculation. Right, let's have a look at adding these up then. For our reactants, then we've only got one item. We've only got the C2H5OH. So that's going to be our minus 278. I believe, yeah, minus 278. Let's stick the units in, good habits. Then for the products, we've got to add some stuff up. So for the ethene, 52.3, yeah, positive number, that one. And then we're adding on to that a negative number, minus 286. So we end up there with minus 233.7. All right, hopefully. Now, when you look at what we're doing, we need to flip the reactants one because we're coming down that side, essentially. But if you didn't do it in the form of a thermochemical cycle, that triangular diagram, you can just write it out. And if when it comes to the assignment you decide to just look this up, what you'll find it doesn't involve the thermochemical cycles, but they do help to show your understanding. Hence, you know, I would encourage you to put them in. What you are more likely to see is something along the lines of that standard enthalpy change of reaction is, well, you have to sum up, don't you? You have to add up on each side. Because you have to come down the left-hand side, if you like, you flip the reaction so that you're going from reactants to elements, then we would put a minus, but it is a sum of all the, what was that, reactants there, wasn't it? So that's going down on the left-hand side, and then we would add on to that the sum of all the enthalpy change of formation for the products. All right. So if we were going to, you know, show it as an expression, you might see it like that. Of course, it's easier to turn that round and put the minus on the other side, isn't it, and say it's the products minus the reactants. So that is usually what you'll see. Whoops. All right, so that's a way of writing it out. If we put our numbers into that, well, our products were minus 233.7. And then if we take away our reactants, which I've lost off the top again, minus 278, so minus 278. So we're looking at, just to remind you, although you know you're using enough maths not to need reminding about that. And we should come out with 44.3 kilojoules per mole. So if that's what you got, well done. If you didn't quite get to that point, then make sure you've got that written down so that you can track all the working through. All right, whoops, slip there. All right, now next thing I'm going to do is to give out the assignment and sort of talk you through some of the bits of that. I know that at the moment the chemistry assignment is not a priority and its deadline isn't until the end of February. All right, so you've got a whole month on that. So today's the last day of January, so you've got 4 whole weeks, right? Your priorities are obviously to get the biology assignment out of the way and to do the revision for that. Once that's done, then, oh, and physics, of course, is urgent as well, isn't it? But once that's done, then the assignment can be, this assignment, you can actually